time on that. That's the latest. There's some kind of the last 7 or 8 years. There's a literature called Compressive Sensing. It's done by some mathematicians. Mathematicians are good, I tell you, because they always work on things we never saw there's any use of it. But because they don't worry about things to be useful, so they think they worry about things which are fundamentally important. So to work out those maths. Once they work out those maths, for example, this compressive sensing math fundamentally is a graph and embedding problem at the end. Is to embed a high dimensional thing into a low dimensional space without changing the distance between one pair of nodes. If A and B is that far after you do the embedding, FA and FB is that far, roughly. These are typical math problem. Actually, is done by some of the people who were probably hundreds of years ago. But lately, people have been doing similar things all the time. So using this distance preserving embedding, we can map high dimensional stuff into low dimensional space. For example, this is a very big X. You can map into a very small X using a random matrix. You map this thing by multiply X to the left by a random matrix. N can be 10,000, M can be 100. You multiply this by random matrix. And it turns out if this matrix is random, you can recover X from Y. If X is sparse. If X only has few non-zero elements here, we can represent X using a very small number of random linear combinations of X. Then from Y, we can recover X. Obviously, you cannot solve for X using Y because you have more unknowns than equations. So what people do is do a minimization. You don't do solution of linear system, you do a minimization. You minimize the error between Y and the 5 times X. Constraint to all the X, which is sparse. So that's the problem we do. And the reason you can recover those X fundamentally is because this matrix is random. If this matrix has enough number of rows, the columns of those places which correspond to non-zeros in X, they are most likely will be orthogonal to each other. They have no coherency because these are randomly selected columns. So no matter where the non-zeros are, the corresponding columns are non-coherent, are mutually incoherent. Because they are mutually incoherent, so the Y can just ignore the other thing and using those columns to cover the X. Okay, so this is not too bad actually. Okay, this is a little more than high school now. Okay, but intuitively is that you can just look for all the non-zero to see which one fits to get a Y. But if you do a combinatorial search, this will become too expensive. You take all the subset of X, you'll be basically doing the L0 minimization, which is very expensive. L0 is counting. L2 will be cheap, and L2 doesn't work, so people use L1. I explain to you why it doesn't work. You use L1, you take a L1 ball is everything on the parameters have the same L1 norm value. Then that L1 ball will look like this. L2 ball like this. L1 balls, the extreme points will be always on the axis. If the variable is on the axis, that means what? The variable is sparse. If a variable x is a vector x1 is on this axis, x1 by definition is like 1, 0, 0. So x1 is a sparse vector. We are looking for sparse vector on this feasible solution. Feasible solution is y equal to 5 times x. So you want to find the minimum red ball which touches this green feasible plane. The minimum one will be the one which is smallest ball, which is still touch the green plane. The touching point must be those corners, right? Once, because the place which touches the feasible plane is on this axis, so those touching points must be sparse. That's what we're looking for. We're looking for x which is sparse, which is still can satisfy the relationship y equal to 5 times x. So this is the reason why you can do L1 minimization. L2 you will not be able to do it. L2 the minimum point could be here, which is not sparse. Once you know you can do L1 minimization, then we can do complex programming, then we can use linear programming to solve the problem. So suddenly we can recover a sparse vector using a small number of random linear combinations of the components of the x. So what we do is we take a input, we take a random linear combination, we add them up. The number of elements here is going to be huge, but you add them up only in small numbers. Maybe this is 1 million, this may be 1,000. Then you use the y to represent x. You can recover x using y. So you have compressed this to a very small number. So instead of working on big data, now I work on small data. I don't work on this one, I work on small one, okay? And this compression is blind. You don't have to do FD. You don't have to do wafer and stuff like that. So it's very, very nice. And people have done a conceptual camera with this. This camera has many pixels, but the number of bits you send out can be so much smaller than the number of pixels on the picture. The bits you're sending out will be linear combination of the pixels. Because the image, as we said earlier, usually is very sparse. You can throw away a lot of things. So you can just take a random linear combinations of this and send a few random linear combinations out. So you really have is a single pixel camera which captures the random linear combination which is done in hardware. You just take a reflection of the image and collect it here, send them out. This collection point is computing the linear combinations all in analog domain. This is a CMOS implementation by somebody else recently. The same idea. You take the random linear combinations, for example, a finger. You can save a lot of storage bandwidth. You don't need an image as big as the original one. You just take the random linear combinations of that. This is all fine, but why this has anything to do with big data? The good news, large applications that I've looked at, they all can be done in that way. You want to sense a spectrum in a radio domain. You have to listen to a lot of people. You want to figure out who is transmitting. You want to figure out the, for example, from an airplane, you want to figure out on the ground who are transmitting, and so on. Let me give you 3 examples here very quickly. The first one is how you actually can use tricks like that to find out in cloud computing which server is running slow. You know, in cloud computing, we sometimes use thousands or tens of thousands of servers running in parallel. Usually, suppose you use a method like a Hadoop or MapReduce, you cannot do the reduce part until the map is finished. And map is done by many servers parallel. If one of them is slow, everybody has to wait. So the earlier you can find a slower server, the better. Then you can replace it with another server. But to figure out which server is slow dynamically, very quickly, you need to monitor them. But how do you monitor them very quickly is hard because you have so many servers running. So what you can do is you just take instead of monitoring them, you just send to a guy to analyze it. Here become a bottleneck. You have many servers, the collection point will become bottleneck. What you can do is instead, you take random linear combinations. The output link here will have the same bandwidth as the input link. You can collect a whole bunch of stuff in by reducing the amount of data you send on the way. Why this works? Because the number of servers who are particularly slow by definition is small. They are sparse. So we can recover those sparse servers using compressive sensing. Here's another example. This problem is getting more and more serious. We are putting a lot of important stuff on hardware which is made outside US. How do you know if there's Trojan? There's some bad stuff people embedded in the hardware. How do you find that? That's going to be an issue, right? So you need to test those chips. But testing chip becomes very expensive because you have to test, you have to go through a lot of test vectors, and you have to look at the output. It turns out the most expensive part is the output. Every test vector there's output. Every test vector there's output. If you have millions of test vectors, millions of output, which will be terribly slow. What you can do instead is you don't take all the outputs. You take linear combinations of the output. So you can compress the thing a lot. So the things coming out will be much smaller. So the output requirements gets smaller. So you can test the chip faster. This is something which is very hot at this moment. I'll give you another example. Suppose the airplane is watching things, radar watching things. Usually today, okay, you believe this. I can do the radar image 1,000 or 10,000 more faster than you can shift the things down. Sensing can be done in parallel, but the data link is fixed. So how do you deal with that problem? You can do a lot of sensing, but then you cannot do an analysis all on airplane. Airplane is limited in size, in power, in everything. So you really want to do is to shift the stuff down, if you can. Then you have to shift the data in the compressed format. Then we could do compressed sensing. We take the linear combinations, which would fit. We only shift a small amount of things down. But here, now you have a compressed the domain stuff. You have compressed data. How do you do processing on a compressed domain? I cannot afford to do processing in the airplane, so I have to do processing here. And here, the guy doesn't even have a computer, maybe have a cell phone. How do you do compressed domain analysis on a small mobile device? Yes, you can do it too. You basically you take this radar stuff, compress into a small cube. You do processing there. the point is that once you can compress the thing by factor 10, for example, because those operations typically is all the n cube kind of operation, you can compress by factor 10, you win factor 1,000 in processing speed. But the issue is that if you do processing on the compressor, how much accuracy do you lose? It turns out, yeah, you do lose accuracy, but if the original problem has enough signal to noise ratio there, some loss of accuracy is okay. I'm getting old, my eyes are getting bad, right? But I can still see. Also, my SNR here is no longer like what I used to have 30 years ago. But I still can see. So the point is, very often you don't need a complete accuracy because the problem you're dealing with has enough signal to noise ratio, so you can afford to do a cheating processing without losing too much. Okay, so these are the tricks, but we don't have to look at the curve anymore. The point is that you will, instead of doing hypothesis test in the original domain, you do a mapping in a compressor domain, then do the processing in a compressor domain cheaply. This is yet another example. This is related to deep learning stuff now. What we're doing when we're trying to extract those information from the scenes, from drug discovery, all this stuff is basically trying to find a good representation, so we can do classification well. We can say this is a real person with a real problem, a chip with a Trojan, or a chip without Trojan. At the end, you need to do the classification. How do people do classification well? It's a matter of representation. If we can do the representation correctly, then we can do the classification right. Easily. You all learn the SVN. Anybody? How many of you learn the SVN? What's SVN? Support what? Okay, you learn some SVN. SVN is a very popular learning method, right? Support vector machine. SVN is a very easy one, actually. It turns out SVN, we have looked at a lot of examples. Primitive learning machine becomes totally successful if the representation is correct. If you already can divide this and represent the objects in the right representation, any stupid defining line is going to be fine. So how do you find the good representations? You do extraction, do feature extractions. You can say this is a chair, this is a table, and so on. So all these vectors here are chairs and tables. The inputs are going to be compared with those guys. So you can do pattern matching. So at the end, we all do pattern matching. Intelligence is about pattern matching. If you can do pattern matching fast, we win. At the very end, okay. So you do the pattern matching, but pattern matching can be very expensive because the dictionary can be huge, the columns can be very long, but we can compress again. We can compress the column into a smaller one, so that the pattern matching is still more or less correct as long as the dictionary entries have enough separation. So we've been doing this. This is quite successful lately. For example, we can compute the sparse representation using compressed domain iterations in the beginning to get certain accuracy. Then in the final step, you don't use compressed domain. You use the whole original thing to do the final refinement. So all the majority steps will be cheap. One big expensive step to get accuracy.